Okay, so good day, everyone. I'm Deepika, and today I'm here to present my research work entitled Secure and Predictive Resource Management in Cloud Environments. First of all, I would like to say many thanks to University of Melbourne, Australia, for giving me the opportunity today to present my work at an international venue. And I would like to share that before this presentation, I have presented my work in Imperial College of London. And let's begin the presentation. My journey of research began in 2014 with Professor R.K. Chauhan Singh, where I worked as a master's student for 6 months for the MTech dissertation. Then I joined Professor Ashutosh Kumar Singh as a scholar in 2015 and officially joined him as a PhD scholar in 2018. And in these years, my research outcomes are these. Till now, I have written 17 SCI papers. Among them, 13 are IEEE and ACM transactions. And tentatively, we are planning to submit my thesis in May 2022. And after that, I would like to continue my passion of research for a couple of more years, and I'm looking for a postdoc position after this. So, outline of today's presentation. Today, I'll discuss about the introduction and motivation related to the conventional resource utilization and its challenges. Then I'll talk about 3 of my proposed work, which we have done in the PhD, and they all are published. Then remarks and summary. So cloud environment. Cloud computing provides shared pool of IT resources to the users across the world. Just with the connection of internet, we get the access of the wide range of services of the cloud environment, and they are always accessible and available anywhere at any time, just with the click of internet. So why we all are moving to the cloud environment? Because it provides a lot of ease and benefits in our life, like rapid elasticity, on-demand self-service, resource pooling, measured services, outsource IT management, which has bring a lot of ease and flexibility in the life of the user. But at the infrastructure, it is suffering from major challenges like resource distribution, load balancing, power consumptions, and so on. Among these, we are going to tackle first 5 objectives in my research work. And technically, they are all belonging to the resource management at the infrastructure level in the cloud environment. So if we talk about the conventional resource utilization, the major problem with the cloud environment is that the resource demands are always dynamic. There is a lot of heterogeneity in the workload, in the service models and the priorities of the user. So this brings fluctuations in the distribution of the load. And this we can observe that there is insufficient management of the resources. Like as we can observe in the figure, most of the times the servers are average utilized. Sometimes they are overutilized and sometimes they are underutilized. So this brings the problem like overutilization, like resource contention problems are there, then underutilization are there. And these problems of inefficient management or inefficient distribution of load brings a series of problems like excess of power consumption. In order to provide the quality of services to the customers, most of the time the servers are kept active and they are not utilized fully, though they are consuming the power and generating heat and carbon and all. In that case, the resources are also getting waste. Simultaneously, because of the resource contention problems or the underutilizations, VMs need to be migrated. So triggering of VMs is there, which creates downtime or the unavailability of services in the real-time environment. And this increases the SLA violations. And overall, if we observe that performance degrades just because of inefficient management of the resources. So to tackle all these problems comprehensively, in my work, we have developed several models, several frameworks to manage these problems. And specifically, we have worked towards 2 approaches. First is workload prediction, and second, efficient resource management. Basically, we have utilized artificial intelligence and some quantum mechanics and the optimization algorithms to develop these frameworks and models. So I'm just letting you with the proposed work now. So this is about the workload prediction. And I would like to share that this was the first work that was assigned to me as my PhD work to develop a quantum neural network for the cloud workload prediction. And after a lot of struggle, we got it published in the IEEE transactions on parallel and distributed systems. And we have developed evolutionary quantum neural network, which is shortly named as EQNN model. So in this work, first of all, the workload is coming from the end users, and it is deposited, the resource usage information is deposited at the repository where we perform the pre-processing, like we have extracted data, then aggregated, then normalized it, rescale that values for the prediction. So this normalized data is divided into training, validation, and testing part. Then to achieve the EQNN model in working phase, we have utilized three distinct stages. So first is the EQNN learning phase. In this, the training data is passed to the model, prediction model, and it is trained for several generations. If we get the desired accuracy, then we move to the validation phase. If the validation, then we pass the validation data and get it checked for the accuracy. To check the accuracy, we have utilized a root mean square error as a fitness evaluation function. Then we move to the testing stage where the unseen data is passed to this model and again check for the valid accuracy. If we get the desired accuracy, then we move to the final stage, that is the load prediction. If when the model is deployed and it generates some resource usage like CPU, memory, bandwidth, number of requests per unit time for the resource management. So this unit can utilize this information and accordingly it can assort the resources proactively at the data center to manage the forthcoming workload in the data center. So now I'm moving to the architecture of quantum neural network. So this is the feed forward neural network, and this was the basic step that I took towards the prediction of the workload. So I have included only 3 layers in it initially. So input, hidden, and output layer. And at each layer, we have used the qubit neurons and connected these neurons with the qubit neural weights. And at the hidden and the output layer, we have utilized quantum gates, basic quantum gates like control NOT gate, rotation gate, and all for the adjustment of the qubit weights during the learning process. Now let me tell you this work in more detail. So the first step is data pre-processing. So first of all, the training data is extracted, aggregated, and normalized using this function. Then at the input layer, the input data is converted into qubits by applying the rotation gate effect. Then at the hidden layer, we generate the qubit vector for the learning process and apply the control NOT gate effect. So this was the mathematical equations that we have generated and utilized for the learning process. So I want to tell these equations in detail. So this F phi is representing a qubit vector, which represents the vector of the qubit weights, the neural weights that we have applied. And this theta is representing the input data that we have transformed into qubits. And this omega is representing the biased qubit vector. If we can recognize that this equation is very much similar to the basic equation that is applied during the neural network learning phase. So we have utilized that basic learning equation for the qubits also and generated the intermediate qubit vector var theta. Then we have applied the control NOT gate effect on this intermediate vector and have transformed the values and updated the neural weights by utilizing the effect of the controlled NOT gate. Basically, controlled NOT gate performs the rotation or the reverse effect on the qubits under a controlled parameter, which helps to update the values of the qubits and help in the learning process by adjusting the qubits as per the requirement. So the same steps were followed at the output layer also. And to get the final output in the range of 0 to 1, we have utilized the sigmoid function. So the output vector of the output layer is passed to the sigmoid function to get the values in the range of 0 to 1, so that we can compare it with the actual values later on and do the evaluation and to evaluate its performance for the prediction. Now, coming to the learning process of this quantum neural network. So we have utilized an evolutionary algorithm for training of this quantum neural network. In this, we have done some modification in the existing differential evolution algorithm. And I would like to say that every evolutionary algorithm works on the population of solutions. So for this also, we have initialized population of qubit networks. So we have initialized n qubit networks so that it can be explored and exploited during the learning process, so that we can come up with the best quantum network for the prediction. So the values were initialized. Then the second step is the optimization. For the optimization, this algorithm works on mutation and the crossover strategies. So we have utilized 3 distinct types of mutation strategies followed by the crossover. But during one iteration, only one of the mutation strategies applied, which helps to update or regenerate the weight during the learning process. So this is QNN optimization phase. And in the bottom steps, we are updating the values and evaluating the network during each iteration, so that we can explore and exploit the population of the networks and get the best network as an optimal solution for the quantum neural network prediction. Now this model, I have implemented this model right from the scratch in Python, and these were the experimental values that were used during the experimentation. And these are the data sets. To evaluate this model on the extensive range of the workloads, we have taken 3 distinct categories of data sets: cluster, web, and HPC workloads. Overall, we have worked on 8 different data sets belonging to these different categories. And this is the characteristics table of different data sets. Now, this work was presented in the extensive manner in the paper, but for today's presentation, because of the time limitation, I'm showing just a few results of the comparison. So this is the normalized root mean square error comparison, in which we have compared the EQNN model with the 7 comparative different methods, existing methods. And this yellow bar is showing the normalized value for the EQNN proposed model. And overall, the prediction error is reduced by 89.87% with the proposed model. We can notice the difference that in case of this back propagation based neural network, the height of the bar is very much higher. So this is representing the difference between the error that we have achieved. Then the second graph is showing the actual versus predicted values for the Google cluster VMs for the CPU and the memory usages. So the black line is showing the actual values of the CPU usage and the memory usage, and the red line is showing the predicted values, and rest of the lines are showing the comparative methods. So we can observe that there is very close proximity between these lines, and the proposed method is very much potent to predict the peak demands as well as the valley points as well for different workloads. Now, this is the result for the high performance grid workload. And overall, the accuracy has been improved by 25 to 95.56%. We can observe the difference as with the SVM, the error was to 69.6 to the power 10 to the power minus 3. And in case of the EQNN, for the same data set, we have achieved the error 10.6. So there is a huge difference which bring this improvement in the prediction model. So then we have computed the error frequency for this work. So maximum time we have achieved the minimum accuracy as compared to the 7 other methods. And overall, it is yielding the minimum error for the maximum number of times as compared. So this proves that the model is valid and it is potent enough to predict the correct requirement of maximum of different variety of workloads. Now, after publication of this work, we have extended this work and have recently developed another model for workload prediction, which is using Hadamard Hadamard gates. So we have named it as a Hadamard neural network. And for the learning process, we have modified the existing black hole learning algorithm in the form of the quantum black hole learning algorithm, and we have done some little modification in between the steps also to provide the better learning of this neural network. But I'm not going to discuss this work in detail because this is under review work right now. I just want to show the highlight of this work. This is the architecture of the model. So this top block is showing the structure of the Hadamard neural network gate, in which we have applied the Hadamard gates in between the layers as an activation function. So this will help in the adjustment of the weight. And basically Hadamard gate provides the superposition action on different qubits and will help in generating the regenerating the qubit values that will help in the learning process of the neural network. Then for the training of this neural network, we have developed this black hole algorithm, which is the quantum based. So quantum black hole has been developed, and originally the black hole has like one phase only, but we have developed it in 3 phases. So there is qubit generation phase, heuristic optimization, and population updation. So we have done modification to improve the learning process of this network. And after that, it is passing the predicted output to the resource management, which will help in the effective or the maintenance of the resources at the cloud infrastructure. So now moving to my second work. So this work is about the prediction with the resource management. So we have named it as OPMLB framework, an online VM prediction based multi-objective load balancing framework for resource management at cloud data center. So this work is also published, and this was the second work that was assigned to me, and it is published in IEEE Transactions on Cloud Computing. So this is the architecture of the framework. It includes 3 phases. So first is the task assignment, in which the user applications are divided into several tasks, and each task are assigned to the VMs for the execution. Then in the second phase, online prediction, the VMs will execute the task, and concurrently there will be the prediction phase for each VM, which will be predicting the resource usage of these VMs for the next interval. This prediction based information will be collected and passed to this cluster management unit. This cluster management unit will analyze this information, and accordingly it will determine any overloading or underloading situation, and it will trigger the migration of VMs accordingly. So this is the load management phase, in which we have worked on the VM placement as well as the migration phase as per the requirement. Now I would like to go in more detail of this work. So this is the first phase, was the task assignment. So in this, the VM selection is done by using 4 different types of VMs: a small, medium, large, and XL. the task requirements are compared with the resource availability of the VMs, and accordingly the VMs are selected. Then for the estimation of the SLA violation, we have used the availability factor. If the offered availability is higher than the guaranteed one, then there is no violation. Otherwise, there is a violation. And if there is a violation, then we have computed the penalty also. Like we have computed it on the basis of the amount of unavailability and the type of different VMs. Accordingly, different penalty cost has been set and it is computed. Then in the second phase, it is the online prediction. So for different VMs, we have set up the neural network, which is a feed-forward neural network, and it contains P input nodes, Q hidden, and one output node, which is also trained with an evolutionary algorithm, which is named as auto-adaptive differential evolutionary algorithm. And this algorithm will help in the learning process by exploiting the population of solutions, and will generate the most optimal solution as an output. Then during each iteration, we have evaluated this model with the root mean square error function. And we have selected that minimum fitness value, means minimum error will be our criteria for the selection of the best solution every time. Then additionally, to combat the losses because of the error in the prediction, we have included one more factor, that is error-driven precaution margins. Each time we are computing this error-driven padding, in which the current error is taken, and some previous errors, previous error and previous prediction errors were included in the form of the error-driven padding. So this will help us to keep the margin during the distribution of the load, so that the problems that occur because of the errors in the prediction, they can be minimized. Then this is the final phase, which includes placement and migration. For the new VMs that have to be deployed on the servers, we have applied the multi-objective VM placement concept, and this is the formulation for that. So this omega JI is there, which represents a mapping between ith VM and jth server. So it says that every VM should be like ith VM should be placed on jth servers, so that it satisfy these three objectives, like minimum power consumption, minimum communication cost, and minimum wastage of resources. For VM placement, there is the resource availability constraint that have to be followed every time. So which says that the resource requirements of the VMs should be lesser than the availability, should be lesser or equals to the availability of resources on the server. Then for the objectives, we have included resource utilization, communication cost, and power consumption. So these were the parameters that were set for the VM placement. And during the detection of any underloading or overloading, we have included the concept of energy efficient VM migration. And this was the constraint for that the resource requirement of migrating VMs should be lesser than the resource availability of the target server. Now this model has been implemented with these configurations. So server configurations, 3 types of servers were taken, which are inspired from the Dell and the IBM server configuration. And 4 types of VMs were set up, and the configuration for these have been taken from the Amazon VM instances. This model, this work is evaluated using 3 different types of the data sets: Google Cluster VM traces, Planet Lab VM traces, and BitBrains dataset. Now this coming to the performance evaluation. So for every workload dataset, we have evaluated these parameters. So this is resource utilization, power consumption, communication cost, migration, and the SLA violation rate. So if we observe that the resource utilization is not changing much with the varying number of the VMs and the varying number of the users, because the resource utilization is independent of the number and the size of the data center. It depends upon the type of optimization, the type of strategies that we are applying during the allocation of the VMs. Then if you observe the power consumption, it is getting increased with the number of VMs. It is obvious because the number of active servers are getting increased each time. Then the communication cost has been evaluated with respect to the interrelated VM, the placement of the interrelated VM. If the interrelated VMs are placed far on different servers, then sure there will be some communication, and number of hops were considered as a distance between different servers, and then we have computed the communication cost and all. Now the same parameters were computed for the Planet Lab VM traces and BitBrains workload. Then we have implemented a multi-objective VM concept. So this is the Pareto front for the multi-objective VM placement, in which this is showing the Pareto front for 1200 VMs of the Google cluster. And the colored balls are showing different VM placement solutions, VM allocations. And these allocations are trying to reach towards a common objective where all the three communication cost, power consumption, and resource utilization may get minimized with the common objective at the non-dominancy level. So they are trying to reach that level. So then we have compared this work with the baseline algorithms like best fit, random fit, and first fit with their prediction and non-prediction versions. So these are the results for the comparison of resource utilization for different workloads. And these are the results for the power consumption. Overall, the resource utilization has been improved up to 62.4% over random fit, and power consumption has been reduced about 69.67% over the first fit allocation. Then we have compared this work with one of the work that is published in Transactions on Cloud Computing. We have compared the total number of unpredicted overloads. So here we can observe from the graph that this is representing the number of unpredicted overload for the proposed work. And these are the graphs that are showing the unpredicted overload for the existing work. So here we can notice the difference that the number of unpredicted overloads have been reduced up to 96.1%. And the reason is very much clear that the existing works have used the Wiener filter prediction and fast up slow down, which are not much good technique for the prediction, and our one was better. We have applied the neural network trained with the evolutionary algorithm. Then we have shown power saving comparison. OPMLB framework is compared with the non-OPMLB framework, where the powers have been saved maximum up to 69% for different workloads, like for the Google cluster, Planet Lab, and the BitBrains dataset. Then this was the OPMLB framework. Now, after that, we have developed some other models for the resource management by utilizing the prediction and the machine learning approaches. So this is one of the work that is developed for the sustainable and secure load management. So this is the architecture of our proposed framework. And here we have set up a green cloud data center, and this is the resource management field that has been set up. So this is managing all the things regarding the security and the energy efficiency, and the machine learning part has been shown here. So, okay, this is another model which we have prepared for the high availability of the resource management, and we have named it as a Shri Hum. So because in this we have we have computed the significance rank of different VMs that belongs to different users. And as per their significance, we do selection of the fault tolerant strategies. So this is the pool of fault tolerant strategies where we match the perfect match for a particular VM. And then we go for the allocation of the VMs according to these fault tolerant strategies. This will help in improving the availability of the services for the end users Then we have made a provision for computing the availability score in this, so that the feedback of the user can be given to the data center, so that the strategies can be improved next time. So it works in the like real-time environment. Okay, now moving to the third proposed work. So this is about the security. So in this work, we have developed a model in which we have talked about how we can secure the workload during the execution in the data center. So this is online secure communication model. And this work is also published in IEEE communication letters. And this is the architecture of the model. So in this architecture, the major role is played by this resource manager and the security manager. So here the resource manager is there for multiple tasks. Like first of all, it will receive the request from the end user and will deploy the request on the data center on different servers. Then it maintains inter-VM communication log, in which it will keep the information of the links, authorized links that for particular VM. In this work, we have assumed that all the VMs that belong to a common user, they are authorized to access each other information, means they are having the authorized links to communicate. And if a VM is communicating with the VM of another user, that is assumed as it is an unauthorized access. So these kind of information is maintained in this IVCL. Then in this work, we have done prediction of the resources also for different VMs. So basically a bandwidth is taken. So bandwidth of VM is utilized by the resource manager. It will utilize this information for the clustering of the VMs on the basis of their bandwidth requirement, so that the VMs can be grouped according to the bandwidth requirement. Like a smaller bandwidth requirement VMs can be placed separately on different servers, and the VMs that which are having the maximum requirement of the bandwidth can be placed on different server, which can fulfill their requirement to prevent any network hog during the real-time allocation. So this was the concept. Then coming to the security manager. So this security manager is there, which will maintain this VLAN. VLAN is a VM link access matrix. So it will keep the information about the links of the VMs, inter-VM links about on the server, which are respective to each server. It is establishing VLAN for each servers, and it is keeping the information of the inter-VM links of the VMs. And to locate any malicious activity, it will compare the information of this VLAN with this IVCL. And if there is any discrepancy or the mismatch of the information, in that case, it will detect a kind of breach, a kind of malicious activity, and it will suspend those links in VMs as well to minimize the effect of the attack. Because whenever there is any security threat, it requires sufficient time to transfer the data. So before the accomplishment of that sufficient time, this act of the security manager will prevent and minimize the effect of that threat. Now this model, in this work, we have discussed about 4 types of attacks related to VMs, like VM vulnerability, hypervisor vulnerability, then co-residency attacks, and network cascading effect. But for the presentation, I've included the concept of only co-residency to discuss this work in like minimum time. So this is the concept about the co-residency, in which we have formulated some mathematical background to compute if there is an attack or not. So here, this omega is representing a mapping between ith VM and the kth server. So this ith VM and the I star VM are placed on a common server K, and they belongs to different users Z and Z star. And this U plus has been evaluated to determine the relation between these two. So for this, We have maintained the authorized inter-VM links, which is maintained by the resource manager in the IVCL, as I told earlier. Then the set of current inter-VM links are maintained in the VLAN by the security manager. And to determine the relation between these two VMs, we will compare the value of this inter-VM links with the authorized inter-VM links. If they are not comparable, if it is not present in the authorized set of links, in that case, there is some malicious act is to be going on. So this value will be 1. So it will detect that there is some illegal or unauthorized relation between these two VMs. So that should be suspended. Now, in the second phase of this work, we have done some work for the congestion avoidance also. To avoid the network congestion, we have worked on the network traffic deviation. So we have utilized the values of the computed network traffic and compared their values with the threshold traffic deviation. And if it is reaching beyond the threshold value, so it means the network congestion, there's a probability of the congestion, so its value will be 1. And if it is below 0, like if it is below 0, it's mean there is no such deviation and all. It's mean in the next interval the traffic would be very less than the expectation. And 0, it's mean that it is a normal traffic, that it will be deviated but within the limits. Then to find out the bandwidth hogs, we have done the clustering of VMs on the basis of their bandwidth usage, so that the maximum bandwidth requirement VMs can be filtered out proactively, and so that to minimize the effect of any heavy traffic during the real-time situation. Then for the VM allocation, we have utilized the same equation, and we have computed the resource utilization and power consumption as well. Then coming to the summary, operational summary of this work. Overall, we have, first of all, we have done the prediction of the VM resource usages like CPU, memory, and bandwidth. Then clustering of VMs is done on the basis of their bandwidth requirement to filter out the network hogs. Then for the security, during the execution time, we have maintained the inter-VM links and find out any discrepancy among the authorized and unauthorized links, and then we have suspended the malicious activities accordingly. Now, this work is also implemented by using the same experimental setup as I discussed for the OPMLB framework, and this work has been evaluated using the BitBrains dataset. Now, these are the results that we have evaluated for this model. So we have compared the results for different number of VMs and for varying number of users, and for different percentages of the malicious users like 5%, 20%, or 90%. We have evaluated malicious links, malicious VMs, the threats, and the network hogs, resource utilization, and power consumption. So these were the matrices that have been computed, and the comparison. This work has been compared with the 3 existing works. So in this, we have compared the network hogs, which has reduced up to 66.46% over in existing work, etc. Then we have compared the authorized links, and they have been increased in the range 4 to 31% over PSSF. PSSF is previously selected server first. This is a work that is published in Transactions on Secure and Dependable Computing. And they have also developed a VM allocation, secure VM allocation scheme, and we have implemented their method at our end, then do the comparison. And then we have compared the average number of legal links that have been increased up to 32.1% over PSSF. Then for security, we have extended and developed some more models. Like this is one of the model which we have developed for the secure and energy efficient resource management. So this top block is showing the resource manager part. So this is the secure load distributor. And the middle block is showing the data center environment. And at the bottom, we have set up a security analyzer and the workload analyzer. So this security analyzer will analyze different types of risks of different VMs related to different VMs, and for different risks we have generated some risk score values, like VM hypervisor vulnerabilities were considered. Similarly, cascading effects and all were considered to generate the risk score values. Then this information will be passed after the prediction of the threat, after the analysis of the threat. This information will be passed to this security alert unit, which will be passed to the secure load distributor. Then the analyzer, workload analyzer, will be analyzing the resource usage of different VMs, and it will be utilized along with the security information to distribute the load in the next session. Then after this, we have developed one model for the VM threat detection. So it is multiple risks based VM threat detection model. So here they are the users who are sending the request, and this is the data center environment. And for this work, we have categorized the threats related to VM in different categories, like VM vulnerability and hypervisor vulnerability have been categorized into configuration dependent threats, and co-residency network cascading are categorized into allocation dependent threats. Along with that, we have used the user records also, in which on the basis of the behavior of the VMs in the previous session, we have maintained different information about the users also. Then historical records of the threats, previous threats are also maintained. So all these factors are contributing towards the prediction of the threat of the VMs. We have generated some score values based on the analysis of different factors, and then these score values will be used for the training of this machine learning model, and then it will generate some output for the threat prediction of the VMs. And as per the analysis, this information will manage the migration of VMs to keep them safe and secure proactively. Then this was about my research work, which we have accomplished for my PhD. And now I would like to say something in general about this research work, that how it is effective for the research lab, industry, and the society. So this work can be used in the real environment. The concepts and ideas can be used to provide the better services in the real environment. Then we can go for some research collaboration at the industrial level also, like with Microsoft Azure and Google, because these days our industries are going to have some collaboration with universities also. So we can go for that thing. Then for the parent institution, we can develop these models in the form of the innovations, in the form of the inventions that can be go for the patent filing and all. So that will be giving benefits to the institution. Then my entire research is belonging to the cloud environment. So I would like to say why the cloud will never die and why the research will never die. So the top 5 research areas of my field: AI, big data, computer-assisted education, bioinformatics, and cybersecurity, they all need the cloud environment, because they need the high-performance computing services, storages for their conduction, for their existence. Then the industries, academia, and research centers, they are depending upon the cloud environment because they want to save their capital, they want to maximize their revenues, and they want to get themselves free from the maintenance of the resources. So it provides a lot of benefits to the user, so they want to enjoy these benefits and will never going to leave the cloud. Then the emerging technologies such as IoT, cyber physical systems, they are forced to use the cloud because they don't have their own processing capabilities, storage capabilities, and for their survival, they are depending on the cloud environment. So overall, what I can say is that it is providing a backbone to the entire field of the technology today and in future also. In the beginning of this session, I talked about the challenges of the cloud environment, but we can have some more challenges in future also. So like previous challenges will be the bottleneck. Oversubscription is there, but in future it may increase because people are, dying towards the quality of service. To get better quality of service, they hire more and more resources, which are getting waste and generating more power and carbon emissions. This is the problem and will be increasing in future also. Then cyber crimes, of course, because the cloud environment is easily accessible by anyone at anywhere. So there could be upsurge in the cyber crimes. Then as per, we know that data is increasing with very high pace. So we need more and more cloud data centers and high speed internet services. And because of these things, possibility of energy crisis could be there in the future. Global warming is still arising and will be the remaining problem in the future also. Then technology is getting advanced day by day. So every day there is a need of lack of expertise is there. This is an incomplete list. So you're free to add some more points to these challenges for the future, which can become the future research problems for the forthcoming researchers. Now, I would like to say something as a summary of this presentation. So in the beginning, I talked about the quantum neural network, which we have developed with using the concepts of the basic concepts of the quantum mechanics and the machine learning. Then secondly, I talked about the OPMLB framework, which is developed for the resource management, prediction-based resource management. Then I talked about the security, how we can secure the load during the execution. So I've discussed about the online secure and communication model to minimize the cyber threats in the cloud area. Then in the meantime, I've also discussed some models. I've shown some highlights about my work, which is at the initial stage, and it is just under review right now. Then my future research plans. In future, I would like to work towards the fault tolerant networks in the cloud network topologies, and would like to learn and explore more the related technologies like edge, serverless computing, and fog computing. Want to read their challenges and develop something to resolve these challenges. Then these days I'm hearing about quantum and post-quantum mechanics, which I want to learn in future and apply these techniques for the upcoming cloud networks. Then till now I have worked in the supervised machine learning area. Specifically, I worked for the neural networks only. So in future, I would like to explore more and would like to learn about the unsupervised machine learning, so and develop some approaches for the cybersecurity cloud environment. So now I would like to wind up this presentation by saying thanks to my research group. First of all, my supervisor, Professor Ashutosh Kumar Singh, Professor and Head, Department of Computer Applications, National Institutes of Technology, Kurukshetra. He led the foundation of my entire work, and he has fostered me to do such a passionate research and grow more and more and reach the milestone and always move ahead. So really, I want to say many thanks to him. After that, I want to say thanks to the experts who have helped me during the revision process and who have improved the responses and have given the expert comments on my manuscripts. First of all, Professor Rajkumar Bhuya, University of Melbourne, Australia. Professor C.N. Lee from National Sun Yat-sen University, Taiwan. Professor Xiongkang Pen from KIT Fukuoka. Professor Vasily Kos from University of Agder, Norway. Then I would like to say thank you to my colleagues. We have got a number of researchers in our lab, but some of them have worked closely to me. They have done the proofreading and all, improved the responses during the revision stages. So I would like to say thank you to Dr. Jitendra Kumar from NIT Trichypilli, India. Dr. Ishu Gupta from National Sun Yat-sen University, Taiwan, and Mr. Rishabh Gupta from NIT Kurukshetra. So many thanks to my research group for the accomplishment of my research work today. And these are the references for today's presentation. Questions, you can ask your questions, and thank you.
So thank you, Deepika, for a nice presentation.
Okay, thank you, sir.
For your research during the last few years, especially picking up the right prominent topics. Not only that, also concluding nicely why this cloud computing research will continue to remain as a green or more fresh and fresh due to various other emerging areas that depend on it. So thank you. So yes, now any of our team members from here, or of course those who joined from there, can please go ahead and ask questions.
Hello, Deepika, can you hear me?
Yeah.
Thank you for presenting us. Very good work. And I have some interest to your first work about the EQN architecture for the workload prediction. My question is why you choose the EQN architecture? Because from the perspective of computer science, you seem to just use the feed-forward neural network and then combine the Q state into the feed-forward network neuron. Have you tried some more complex neural networks? Just for example, like Q quantum reinforcement learning, which has been found by some physics and published in physical letter review, and also other probably better quantum neural networks have been invented. And have you tried the more complex one to advance your experiments?
Okay, thank you, Ming. Can I say something?
Yeah. You see.
Okay. Okay. I welcome your suggestions. That these days we have got Q states and all that I could have included. But as I told, that this was the first work that was assigned to me as a PhD scholar. And at that time, I was having a nil knowledge about the quantum and the machine learning. So at that stage, I just started reading the basics and started implementing the concepts, whatever I was getting at that time in the Python, right from the scratch. So as per my knowledge at that time, around 2.5 years back, so I just worked whatever I was having at that time and build up this model. And right now I have gained much knowledge and the suggestions that you are telling me these days that I could have go for more advanced techniques and use the existing works also. But what I feel about my work is that whatever I did, it was my own, and I'm very, I can proudly say that I did this from the scratch. So I'm much confident about the EQNN model, whatever I have done at that time. These days, the things have become much easier that we can use the existing libraries and all. Definitely to improve my work in future, I will include these kind of existing libraries to get the better results and all. And I welcome the suggestion, whatever you have told me right now, for utilizing the quantum techniques for different aspects, like for the cybersecurity and all. So in future, I'll try this one also. So thank you for your question.
Okay, thank you. And I also think there are also some improvement for the tuning algorithm. And in this paper, you use some probably heuristic algorithms, and I think there should be further improvement to probably some advanced training algorithms. And I have read some papers in Nature or Science. They publish such kind of training algorithm. And for the second question, do you have any other tricks? For example, just like combining the Q state into the feed-forward neural network. I think this is just like a trick. And do you have any other suggestions for the tricks for using quantum neural networks?
Yep. Actually, this can I answer, Deepika, for you?
Okay.
If you don't mind, just allow me to answer this young man. See that what I understand about your question. There are two processes. The first process is from bit to qubit generation. So from bit to qubit generation, we can use different kind of transformation. Like you
transformation.
can use, like,
Like this.
yeah, C0 and like
Okay.
Hadamard, Pauli, so many transformations are there. And every transformation has different kind of importance. For example, if you want to go for multiple inputs, then you can use Toffoli and all. If you want to go for the single input, then of course you can go with C0 and Pauli and Hadamard. After transferring this to the qubit, that is the first part, then training parts comes in the picture. So you have to see that which training algorithm is well suited for the quantum. So for example, recently we used like black hole theory. Even a lot of theories are already existing, which no one could use so far. Like physics, you can get a lot of theories. And then after this, you can use for the training. Of course, you may not get better result. I don't give guarantee for better result. But as a theoretical contributor, as a researcher, as an academician, yes, we can say that this is my contribution. This is the place where we have contributed. Because generally when we apply ready-made like libraries, that libraries are good for non-computer researcher, like civil engineering, mechanical engineering. They can use the libraries and all, because for them, result is the more important point. But what I understand is that as an academician, we should have some kind of theoretical improvement also, so that maybe we can have some existing algorithm and we can use for training and we may get better result. Of course, it is a very, very time consuming. And in that sense, I can say that Deepika was very hardworking and she used to take challenges, these kind of challenges. So whatever the idea comes in my mind, I used to pass her and she has courage to take these challenges. So these two places you can do contribution.
Okay, thank you. Thank you for your insights and explanation. Very thank you. Okay,
Good.
these are my questions. Thank you.
Deepika.
Yes, sir.
Deepika, am I audible to you?
Yes.
I got one idea here. Like maybe once you come tomorrow, I can give you physically. The way you are saying that IoTs and all, they are forced to use cloud. Now we have to identify some kind of IoT applications. Which type of IoT devices are still capable to generate, process their data without cloud? How many type of IoT application has that they have to go on cloud? We can give these kind of like some graph or table in introduction so that we can convince the researcher that yes, the cloud is the only option for cyber physical system and IoT devices. We can give some kind of like reports or parameter. If it is available, is okay. If no, then we have to generate. That's my quick idea came in my mind. And I think I'm done. So Professor Buya is here. So I always follow his. Last time, sir, you came here and you gave some idea. You forget basically. Maybe something networking and all. We incorporated networking problem also. And we published a couple of papers based on that. So your expert comment is very, very important for us because our new students are also sitting here. They are going to work for another couple of years with me, so they can grab the idea, whatever the idea you have.
Yeah, sure. As Deepika you mentioned about this IoT applications, one is the default model is to use cloud environment for supporting IoT applications. When you come to IoT applications that are in real time in nature, that requires real time response in very low latency, maybe a few microseconds. So there, this idea of using compute capability at the edge of the resource and also some of the compute capability within the device itself need to be harnessed along with cloud as necessary. So cloud may be not available all the time, but there you can use their resources. Plus, the benefit is by doing this, you can reduce the load on the network itself. So this aspect of network hog, which Deepika also discussed within the cloud environment. Now, when you go for across cloud environment, across IoT applications, including like this smart transport system, driverless cars and vehicles, these are the futuristic kind of applications, smart transport system. So there, these thoughts play a very, very important role. Then obviously the network, I mean, the security cannot to be, is an open network environment. So one is this network hog management through using SDN, where you can do network slice allocation. So so that means some users are not allowed to go beyond certain limit. So if they were hogging the network and consuming too much of resource, then at that time there's a need of this QoS or a network slicing, so that other users that are critical can gain access to resource. Yeah. So there are a number of these open challenges that come into picture when you really move towards IoT with mobility and applications such as smart transport and the many other applications with this mobility is coming into picture. They can be in smart city, smart transport, and when you bring in the driverless vehicles, it is going to be even more huge challenge. So others, any other questions? You can unmute and ask. Deepika, you can maybe that unshare the screen so that we see more view of participants.
Yeah. Like our side also, like an IT Kurukshetra side, this some members are there. You can have some question if you have in your mind.
Yeah, hello. Thank you very much for your presentations today. Actually, I started working on quantum computing last year, and I just learned the basic about quantum computing. If I know the quantum computing have three important characteristics. First is superposition, entanglement, and interference. But at the first work, you mentioned about evolutional quantum neural network. I wonder, are you using C0 gate and a Pauli Y rotation gate? Yeah, I wonder which characteristics of quantum computing you leverage to get advantage to compare with classical solution in the your first work. Yeah, can you guess my question?
Actually, I'm not able to understand what you are actually asking. Can you pardon?
Yeah, I mean, in your first work about quantum neural network, which characteristics of quantum computing are you leverage to get more advantage to compare with the classical one? Why you choose quantum computing to improve the neural network? Yeah.
Okay, if we compare the quantum neural network with the classical learning, what I found during the experimentation is that during the classical neural network learning, we utilize the real number weights as the neural network weights, and we adjust those weights only during the training process. But if we go to the quantum, we apply the quantum mechanics. If we execute like qubit weights and all, in that case we get more diversity. The population of the solution is get more diverse, and it brings more optimization during the learning process. So because of the most optimal result during the learning process, we get the better prediction as compared to the classical neural network. Because with the qubits, basically to implement the qubits, have utilized the complex numbers generations, and then we have transformed that by applying the superposition concepts, and also during the adjustment of the weights, it has increased the diversity. So more exploration and more exploitation of the existing population could be done with the usage of the qubits and the quantum gates concept, as compared to the classical learning, where we work in only like a limited range of numbers and all, and then we used to optimize the neural network. So this is my like personal experience. Yeah.
Yes.
Can I just help you? Can I just help Deepika, if you don't mind?
Okay, sir.
Yeah. Like whenever we go for classical learning, we just play with the bit basically, and the bit representation is either in form of 0 and 1. Of course, they are computationally simple to represent. When we move to the quantum, the value can be between 0 to 1. Any value can be between 0 to 1. Of course, the mathematics behind that, we have to use the complex gates, this complex numbers and all. And because of this, of course, all the quantum learning need more complexity, but accuracy wise, since we have like a range basically between 0 to 1, and then getting the best value between 0 and 1 is, the chances for getting best values are more. Of course, the process takes time, it is complex. That is the reason quantum learning is the future of all this machine learning concept, I can say. Only one obstacle we have, we are using this quantum learning, but running on classical computer. Once the hardware side supports and we start running our algorithm on quantum computer, of course, the result will be better. Plus computational complexity also we can reduce significantly. So that, like, it's a trade-off between these two. So that is the reason we are not going through classical learning.
Yes.
Am I able to convince you?
Yeah.
Am I able to convince you for classical to quantum?
Yeah, thank you. But what I wondered is, I usually see the variational neural network is a popular quantum neural network. That's many other people. I usually see that you Hadamard gates in variational neural network. But I wonder, how can you use a CNOT gate and rotation gate to generate like superpositions to leverage some advantage of quantum computing? Yeah, in the quantum neural network.
Okay, I got your question. What you are asking is how we can go for the implementation of these things. So, okay, in the presentation, I told that we have taken the input data and normalized the values of the data samples, which are in the form of the real numbers. Then we have applied the rotation gate concept, rotation gate effect. So by applying the rotation gate effect, we can, by multiplying it with the 90 degree, like pi by 2, we have transformed this data into a qubit form. And to generate the neural network weights during the learning process, we have applied that qubit generation equation, the mathematical equation for that. And this will help in generating the qubits by applying, by computing the magnitude of the complex numbers that were generated during the random allocation of the population. Okay, so for the generation of the qubits, we have applied the concept of rotation gate, quantum rotation gate. And the controlled NOT gate was applied as during the activation at the hidden layer and the output layer. So the control NOT gate, basically it works under a controlled parameter. So its function is to reverse or sometimes like non-reverse the values of the qubits. To reverse the values and to get the control parameter, we have utilized a random number as a control parameter. When it is generating the value 1, in that case, the qubits will be reversed. Reversed means we have applied that negative effect. And sometimes it is when it is 0, then it is not reversing the values. So during the learning process, the qubit values will be updated during the iteration. And to evaluate each time the performance of the network, we have applied the fitness evaluation function. And for this case, we have used the root mean square error as an evaluator of the entire network. So every time we are selecting the network which is giving the minimum error. So the population will be updated in the direction of the minimum error during the learning process. So this will help at that phase. So the summary is that rotation is applied for the generation of the qubits, and control NOT gate is applied during the activation at the hidden and the output layers. Okay.
Yes, thank you.
Okay.
Thank you.
Hi, Deepika. So I
Yes.
wonder which physical device did you use to train and test the equivalent?
Physical device?
Yeah, the physical. Did you use simulation
No,
or physical device?
No, I have simulated the environment, and I have simulated the concepts of these gates to train the current network model. So personally, I cannot say about anything physical because I have not used any physical devices during the development of this model. Okay. I think what my supervisor can say, because he belongs to the field of electronics also, so he can say something in this respect.
Okay, so
yeah, this you passed very big question basically. Like I can tell that so far there is no quantum computer available in the lab. IBM generated one lab for one quantum computer, which is just only 30 qubit, and which is available online, like our cloud environment. We can run the programs and all there, but so far we didn't use. I'm expecting that maybe after 10 years in our lab, we can have like quantum computers, hardware side, all basically the physics people, how they are going to support us. Of course, we can give theory like we can develop the gate, we can minimize the circuit, we can design the chip basically, but that chip should be basically supported by the material science people, and just we are waiting for that. And even I got the same question when I was in University of Tokyo, I think in 2018. One professor asked me that I'm okay with your all theoretical background, but can I see quantum computer before I die? The answer was like, still we are waiting for others to, like material science people, physics people, to come and interpret our ideas the way like we develop circuit at digital level, and then semiconductor people like came, and then after that the this FET and this transistor technology they applied, and then we got hardware. That kind of things still we are waiting. So we are not using any kind of hardware, just all simulated base. Of course, we have some GPUs. Theoretically, we just model data we have taken, converted into the qubit form, and that qubit form we have applied for the training. But running wise, we are using classical environment.
Okay,
I hope.
So yeah, so since you are using simulation, how long would it take to train the network? Would it be longer than the traditional way, or it will be shorter than the traditional way to train the similar side of the neural network for the same data set?
Of course, theoretically it should be more. But again, sometimes depends on machine. Sometimes depends on machine configuration. Like if you are using higher version of machine,
I mean on the same machine, same CPU, same GPU,
yeah,
same
machine.
RAM.
Of course the quantum is taking more time.
How long?
Deepika, you have some kind of complexity comparison?
Sir. Yes, sir. We have shown that comparison in paper also, but right now I can just, do I need to share the screen to tell that, or I can
just a number is enough.
Tentatively how many, like
but
flow means
tentatively I can say about 6 to 7 times it is higher than the real traditional environment. But when I experimented, the time consumption was higher than the traditional neural network training, but with comparison with the ARIMA model, I have also done comparison with the ARIMA model, the training time was lesser for this proposed work. Yeah, this was my experience. And this is Deepika, paper also.
Deepika, you try to understand question from Professor Dan. ARIMA is very old technology. ARIMA is very old model. So if we are beating ARIMA, it's not good. we have to beat the latest work. So I can tell you in the short form that of course our training time is more. Only one case we can just say that some of the training is basically offline. It's a kind of offline exercise. So we can say that, okay, our accuracy is more important than computation time. Even we are taking a lot of time, it's okay. 5-6 times we are taking, but accuracy wise, we are better than the classical. And that place, accuracy is going to play a big role. That argument we have here to sell our research.
Yes. Okay, thank you. Thank you for your answer.
Any questions?
So I think let us stop bombarding on Deepika. Yesterday night she is preparing, and so, sir, if any no question, then we can have we can close the loop of discussion today.
Yes, yes. So thank you very much, Deepika. Thank you, Ashutosh, and the team for joining.
Can we continue? Some other students are also encouraged.
Yes, yes.
Can we continue this presentation? Maybe monthly, at least we can do this kind of presentation.
Yes,
Some
yes,
other
definitely.
students, they are also excited to give some their work, to show their work. So maybe next month we can plan one student.
No problem, no problem.
Yeah,
Definitely.
one student is working on data privacy and all. This Dr. Jatinder is also working on prediction.
Sure,
So
sure, no problem.
some kind of like knowledge sharing we can do.
Sure, definitely, definitely. So we can maybe later on, once we finish the implementation of quantum functional service, we can also do the same thing and also show you the demo of execution of some of this work on real quantum systems, that
Yeah.
IBM quantum system, and also we're trying to connect with others as well. So hopefully we can show you the practical. I think these are the questions like, so if you have a quantum model, so theoretical, the same quantum model, if it is mapped to a real quantum system, then obviously that will be fast. There maybe the decision will be much faster. And that is another way of benefiting from real quantum machines. Yeah. So
Okay,
yes, so thank you. We will do that. So as you suggested, and we
thanks a
will
lot. Nice to meet your research group.
yeah. So thank you all for joining.